welcome to the Deep Dive. Today, we're diving headfirst into a topic that's not just growing, but fundamentally reshaping the very way we build technology.
Yeah, it really is.
If you've grappled with the ever-increasing complexity of modern software, I mean, who hasn't, right? And you've seen the rapid advancement of AI tools, these forces are converging.
Mm-hmm.
But what if that convergence isn't just about automation, making things faster, but about a truly transformative partnership?
That's precisely it. It's a profound integration that goes far beyond just simple code generation.
Right.
In this deep dive, we'll explore how AI is evolving into, well, a genuine partner in software engineering. We'll unpack some powerful new frameworks that enable this collaboration, examine the indispensable human element in this changing landscape, and that's key.
Absolutely.
And address the critical need for robust governance and auditing as these AI systems gain more autonomy.
And to guide us through this intricate landscape, we're pulling insights from a really rich stack of sources you provided. I mean, we've got everything from discussions on unified command line interfaces and the cognitive science of AI.
Yeah, the cognitive side is fascinating.
All the way to the ethical implications of AI autonomy and its significant impact on creative industries. It's a lot to synthesize, but the insights are genuinely profound.
Our mission today, really, is to uncover how these diverse pieces fit together into a cohesive vision, a vision for what's being called a modular intelligence ecosystem for software.
Modular intelligence ecosystem.
Okay. And more importantly, we want to explore what this means for your role, whether you're a seasoned developer, an architect mapping out future systems, or, simply someone deeply curious about the cutting edge of technology.
So get ready, because we're about to explore the future of coding in a way that might actually surprise you. So let's begin by exploring the automation layer, orchestrating AI with unified CLIs. It often feels like we're juggling, a dozen different AI tools, each with its own interface, its own quirks.
Oh, definitely. It can be incredibly fragmented.
Yeah. But our sources, they paint a picture of something much more unified, this modular intelligence ecosystem. What's the core vision behind this unification?
Well, what's truly compelling here is that drive, that need to move from fragmentation to unification. Just think about your current workflow, right? You might be hitting separate APIs for Google's models, Anthropic's Claude, OpenAI's GPT series. Each one has its own syntax, its own authentication hoops to jump through.
It's like having a different remote for everything.
Exactly. A different incompatible remote control for every smart device in your house. It's maddening. Our sources highlight this inherent desire to bring all these diverse AI capabilities into a single cohesive workflow, allowing developers to seamlessly orchestrate them for complex tasks. And this isn't just about convenience, though that's nice. It's about enabling a whole new level of programmatic control and integration.
So the goal is really to eliminate that constant context switching, that mental overhead.
Yeah.
It sounds incredibly empowering.
It is.
Now, our sources mention something called the trifecta of research that serves as the foundation for this kind of AI development. Can you maybe elaborate on those three core components?
Absolutely. Think of this trifecta as the foundational pillars upon which you build this advanced modular intelligence ecosystem. It gives you the complete picture.
Okay, pillars.
First, there's the theoretical framework. This is exemplified by a resource like the Foundation Agents repository.
Yeah.
Now, this isn't executable code itself.
Right, not code.
No, it's more like a scholarly, curated collection of papers, conceptual models, architectural diagrams. It's the why behind AI agent features. It provides that deep conceptual and architectural understanding you need for informed design decisions. It's where the fundamental principles of agentic behavior are explored and documented.
So that's the blueprint, the academic underpinning, the theory. What's the next piece?
Yeah.
The one that takes us closer to actual practical application.
Okay, next up we have the open source engine. Our sources illustrate this with something called OpenManus. This is a concrete Python-based agentic framework.
OpenManus. Okay, Python-based.
Exactly, and it's designed specifically for deconstruction and integration. It lets you, peek under the hood and really understand how these agents function in practice. Crucially, OpenManus is built to connect dynamically to MCP servers.
MCP, Model Context Protocol.
That's the one. Model Context Protocol servers. This means it can expand its toolset and its capabilities on the fly without requiring direct code changes. It gives you this transparent and adaptable implementation layer. It's pretty neat.
Okay, so we have the theory, then the open source implementation that can talk to these MCP servers. What completes this puzzle? What's the third leg of the stool?
The third piece is the unified GUI, or graphical user interface. A prime example mentioned is LibreChat.
LibreChat, got it.
This is a really feature-rich web interface. It basically stands as a proof of concept, demonstrating the viability of multi-provider extensible AI models. LibreChat supports various AI providers: Anthropic, OpenAI, Google, even custom endpoints you might have.
Wow, okay.
And it incorporates powerful features like a secure, sandboxed code interpreter API and comprehensive agents and tools integration, including, importantly, that MCP support we just talked about.
Right.
So it effectively demonstrates how a single interactive interface can manage and orchestrate a vast array of AI capabilities, specifically for human users interacting directly.
So we have the theoretical grounding with foundation agents, the practical open source engine like OpenManus, and the unified graphical interface, LibreChat, for human interaction. Makes sense. But where does the unified command line interface, the UCLI, fit into this modular intelligence ecosystem? It's described in the sources as the essential fourth component. What makes it so crucial?
Ah, yes, the UCLI. While LibreChat is fantastic for interactive use, for clicking around and experimenting,
Yeah.
the UCLI is the automation and scripting layer. That's what unlocks the true programmatic power.
Okay, automation. That's the key.
Precisely. It's essential for things like automated testing, integrating AI into your CI/CD pipelines, embedding agentic capabilities directly within other applications or scripts, all from the terminal, without needing a human clicking buttons.
Right.
Imagine directing a high-level planning task to, say, Claude Opus, then handing off a specific code generation snippet to Codex, and maybe sending a data analysis query to Gemini, all within the same script or work item, seamlessly orchestrated by the UCLI.
That sounds powerful.
It really is. The UCLI is like the silent conductor behind the scenes, ensuring consistent, repeatable, AI-driven workflows.
That distinction makes perfect sense. It's about leveraging the unique strengths of different models programmatically for specific parts of a larger task. But building such a UCLI, I mean, that sounds incredibly complex given how different all these AI APIs are.
Hmm.
What are some of the core design considerations and challenges there?
Oh, it's definitely not trivial. This is where the real engineering challenges come into play. Our sources highlight several major hurdles. First, you need a unified command structure.
Okay, unified commands.
And this isn't just about simple aliases, right? It means designing clear, intuitive syntax that completely abstracts away the underlying API differences.
So like instead of remembering OpenAI this flag and Claude Clay that other flag.
Exactly. Instead of separate commands like OpenAI Chat Model GPT-4 and Claude Clay Query Model Claude 3 Opus, you'd have a single, consistent command structure. Maybe something like a query summarize this document model Claude, or accode generate a helper function like Python model Gemini.
That's much cleaner.
It is. And one source notes that the real analytical power, the true research capability, comes from commands like iCompare. How would you approach this problem? Models, Gemini, Claude.
Oh, interesting. Side-by-side comparison built in.
Yeah, allowing direct side-by-side evaluation of different models reasoning on the same prompt. This unified approach vastly simplifies scripting, automation, and even just daily use.
I can certainly see how that streamlined syntax would simplify scripting. Definitely. But how you securely manage all those different API keys for the various providers, that sounds like a potential security and logistical nightmare, especially in an automated environment.
You're touching on a critical security concern: authentication management. Absolutely vital. The UCLI needs a robust and secure way to store and access API keys for all these different providers.
Yeah, you can't just hard-code them.
No, please don't. Common solutions, as suggested by our sources, involve things like encrypted configuration files, maybe stored securely in .configunified click-credentials.yaml, or leveraging system environment variables like Gemini API Key or Google API Key.
Standard practices, okay.
Standard, but the design must prioritize security above all else, especially when you're integrating this into sensitive automated pipelines like CI/CD. Compromised keys could lead to, well, significant vulnerabilities or massive cost overruns.
Yikes. Okay, so you handle the keys securely, but then you get responses back from these diverse models, and they all have their own unique JSON structures, different data formats. How do you handle that mess?
That leads us right to the essential challenge of output normalization. It's a big one. Every AI API returns data in a different JSON structure, each with its own quirks, its own conventions.
Yeah, I've seen that. It's all over the place.
Exactly. So a core function of the UCLI has to be parsing these varied responses and presenting them in a standardized, consistent format. This is absolutely crucial for creating auditable, quantitative outputs, especially if you're doing research or automated analysis.
Makes sense. You need apples-to-apples comparison.
Precisely. For instance, every response could be wrapped in a consistent JSON object containing standard metadata like model ID, timestamp, token usage, and the normalized content itself. This makes it effortless to compare, analyze, and log outputs from different models for performance tracking, cost analysis, whatever you need.
This all speaks to a significant effort to manage and standardize various models. Now, our sources frequently mention the Model Context Protocol, or MCP. We touched on it briefly. How does MCP help standardize this, and what's its role in this whole unified ecosystem?
Okay, MCP. It's really central to Claude's approach, which one source describes as very protocol-centric.
Protocol-centric.
Yeah. In this model, an AI agent's knowledge and capabilities aren't seen as innate, like built-in things. Instead, they're acquired through formal communication with external entities via MCP.
So it learns by talking.
In a way, yes. Think of MCP as a kind of universal communication standard, a common language, letting AI models talk to any external tool or service that also speaks MCP without needing a custom translator every single time.
Like a universal adapter.
That's a great analogy. This design strongly favors interoperability and modularity. It essentially separates the AI's core mind from the world of tools it interacts with. MCP is the standardized bridge between them.
Okay, so it's like a universal adapter for AI to connect to the outside world's tools.
Precisely. And our sources provide a really good example with the Gitkraken CLI, the GK CLI.
I get cracking.
Yeah, it actually serves as a local MCP server. It wraps common actions for Git, GitHub, and Jira into this MCP framework.
Oh, interesting. So it exposes Git and Jira actions via MCP.
Exactly. This means it can directly provide a rich set of tools to LLMs for interacting with Gitkraken APIs and the underlying Git or Jira functionality. The real power here is that your AI agents can immediately leverage the GK MCP server without you having to build complex custom wrappers for Git operations or Jira ticket management from scratch.
That's a massive shortcut for developers. Huge.
It dramatically accelerates the development of capable AI agents that need to interact with version control or issue tracking.
So the UCLI we were talking about, it essentially acts as a manager or a host for these MCP connections.
Exactly right. The UCLI acts as an MCP host. Its core framework manages these MCP connections, allowing new plugins or tools to simply define their capabilities and then pass the necessary context through to the model API using the MCP standard. This creates a truly unified tool ecosystem where different AI models, even from different providers, can access a consistent set of external capabilities, all managed and brokered by the UCLI.
That's key.
This is absolutely key to building complex multimodal AI applications where the AI needs to interact with various external systems in a standardized way.
That's a significant architectural differentiator. Now, our sources also highlight some really fascinating epistemological differences, basically, how they know things between models like Claude and Gemini, particularly in how they approach tools in context. Can you elaborate on that distinction? It sounds quite deep.
It is a nuanced but really crucial point, and it hints at fundamentally different philosophies in AI design. Claude, as we've noted, is fundamentally protocol-centric.
Right, the MCP focus.
Exactly. Its design prioritizes explicit communication and modularity through MCP. Its security posture is typically cautious by default, often requiring explicit user approvals before it takes certain actions.
Okay, cautious.
And it uses things like .dxt extensions for securely packaged server execution, where all the dependencies for a tool are bundled together safely. This means Claude relies heavily on clearly defined external contracts and external tools for its capabilities. It's like a skilled conductor directing a diverse orchestra through very precise scores, the MCP protocols.
Okay, so Claude is more about precise external communication, interacting with defined tools via protocols. How does Gemini contrast with that?
Gemini, on the other hand, seems to embody a more integrated agentic framework. Instead of seeing itself as a distinct entity communicating with external tools, Gemini is conceived more like an integrated body, which, in this context, could be the CLI tool itself that possesses a rich set of innate capabilities.
Innate capabilities, built into...
Kind of. Its understanding of the world and how to act within it is shaped by a layered system of instructions and configurations. You have system-level defaults, user preferences, project-specific settings, even localized subdirectory configurations that can influence its behavior. This creates what our sources intriguingly call Cultured AI agents.
Cultured AI agents. That's a fascinating phrase. How does that layered configuration actually manifest in its behavior? What does it do differently?
Well, Gemini uses its innate tool set, things like the ability to run shell commands, read files, edit files autonomously as part of its internal React cycle.
React, reason, act loop.
Exactly, the established reason act loop where an agent thinks, plans, takes an action, observes the result, and then thinks again. So for instance, if you task Gemini with fixing a bug, it might formulate and execute a complete plan entirely within its own body.
Also,
It could decide to run shell command to execute tests, see them fail, then read file to analyze the error messages, figure out a correction, use its edit capability to modify the relevant files, and then rerun the tests using run shell command again to verify the solution.
all internally.
All is part of its internal reasoning process before it even presents a concise summary or the fixed code back to the user. This layered configuration gives it a more nuanced worldview, almost analogous, the sources suggest, to how human societies transmit cultural and institutional knowledge through various levels of rules and conventions. It's designed to be a more proactive, intrinsically capable partner within the developer's environment.
Wow. That truly shifts our understanding of AI's role, doesn't it?
Yeah,
It's not just about what the AI does, but how it fundamentally thinks and interacts with its environment.
precisely.
And that brings us perfectly to our next section, the developer's new brain, AI as a cognitive partner. This sounds huge. Let's start with the foundational concept. What exactly is an engineer's mental model in the context of software development? We use the term, but what does it really mean?
It's a great place to start. When we talk about an engineer's mental model, we're referring to an internal cognitive representation of how a system functions. It's like a simplified, abstract tool they build inside their mind
Okay, an internal tool.
that helps them comprehend, create, and manipulate these complex, often intangible software systems. It's not just knowing the syntax of the code, right? It's understanding how components relate, how data flows through the system, how the underlying logic behaves, how it interacts with external dependencies. It's their internal explanation, their map of the system, essentially.
So like an architect's internal blueprint, constantly evolving and maybe a bit fuzzy around the edges.
Exactly like that. And these mental models, they're often iconic and analogous, meaning their structure broadly corresponds to the system they represent. They're truth-based, they typically reflect what's possible and true within the system, but they also need to be flexible enough for crucial what-if scenarios, which are absolutely vital for debugging and design work.
Or for troubleshooting.
Crucially, though, our sources emphasize that these models are both ephemeral and incomplete.
Ephemeral, meaning they fade.
They can fade, yes. And incomplete, no two engineers will have the exact same mental model of a complex system. Plus, an individual's model evolves over time as they learn more, but it can also decay if they step away from the system for a while.
Ah, I felt that.
Haven't we all? This ephemeral nature creates significant challenges for long-term maintenance, especially when a senior developer leaves a project taking invaluable unspoken knowledge, their unique mental model, with them.
That's a powerful point about how fragile that knowledge transfer can be in a team.
Yeah.
The sources also mention the notional machine. What does that add to this concept of a mental model? Is it part of it?
It's a key extension of it. The notional machine is the abstract computer or runtime environment that's actually executing the code.
Yeah.
A good programmer's mental model extends beyond just the source code itself, to include this abstract understanding of how the computer processes instructions, manages memory, handles concurrency, along with business logic, system dependencies, user interactions, the whole nine yards. The accuracy and completeness of this comprehensive mental model code plus notional machine plus context are directly correlated with superior programming performance.
So it's not enough to know the code. You need to understand the invisible machinery that brings it to life.
You absolutely do.
This all sounds like a tremendous amount of mental work, just holding that model in your head. And our sources delve into cognitive load, a concept from psychology that seems absolutely central to understanding developer productivity. Can you break down the 3 types of cognitive load they discuss?
Yes, cognitive load theory is crucial here. It's really key for optimizing how engineers learn and perform. It breaks down the mental effort required to process new information into 3 distinct types. First, there's intrinsic load. This is the inherent difficulty of the task itself, the essential complexity of the problem you're trying to solve. For example, designing a completely novel algorithm for a complex machine learning model would naturally involve high intrinsic load. There's no getting around that core difficulty.
Okay, so the core challenge itself. That makes sense. What about the other two types?
Second, we have extraneous load. This is the mental effort spent on non-essential information or, frankly, just poor design.
Ah, the useless stuff.
Pretty much. Think about deciphering confusingly named variables, navigating convoluted dependency paths that seem to go nowhere, or dealing with excessive boilerplate code that adds absolutely no real value to solving the actual problem.
We've all been there.
Right. This is wasted mental energy. It doesn't contribute to understanding the core problem, and it certainly doesn't help you build expertise. It's just friction in the system. Unnecessary friction.
And finally, there's the productive kind of load, the good kind.
Yes, that's germane load. This is the productive effort. It's associated with learning and building robust long-term memory structures, what psychologists call schemas.
Schema, right.
It's the mental energy dedicated to deep understanding, to recognizing patterns, to connecting new information with existing knowledge. This is what ultimately leads to true expertise and innovative problem solving. It's the load involved in actual learning and mastery.
So it really is a zero-sum game then, isn't it, based on those descriptions? If extraneous load is high, there's just less capacity left for the valuable intrinsic and germane load.
Precisely. It's a finite resource, your working memory. Every unit of mental energy an engineer spends struggling with extraneous load directly reduces the capacity available for tackling the intrinsic complexity and engaging in germane learning.
And that creates a vicious cycle.
It creates a destructive chain, really. Poorly structured code, unclear documentation, confusing abstractions, they all increase extraneous load. This then reduces the mental capacity to grapple with the actual problem, intrinsic load, and to form the schemas needed for long-term learning, germane load. The result: slower problem solving, more errors, and diminished skill acquisition over time.
Wow.
Our sources strongly suggest that the most effective software engineering practices, and by extension, effective AI assistance, and even advanced AI prompt design, must ruthlessly focus on minimizing that extraneous cognitive load.
Okay, this is where it gets incredibly compelling then. If AI can help minimize that extraneous load, it effectively becomes a cognitive prosthetic. How does that work in practice? How can AI actually do that?
AI can directly reduce extraneous load in numerous ways. Think about it. By generating code that follows explicit naming conventions, uses minimal indirection, has clear module boundaries, and significantly reduces boilerplate. AI handles the rote, mechanical aspects of coding, the stuff that consumes mental energy but isn't core to the problem, instead of a human engineer spending precious working memory cycles on these low-level, repetitive tasks.
Like setting up a class structure or something.
Exactly. The AI can handle them, freeing up the human's cognitive capacity to focus purely on the problem's intrinsic complexity and the germane learning involved in understanding the domain and the solution. Imagine the boost to productivity when your mind isn't constantly bogged down by that repetitive setup and syntactic trivia.
So it's about making the code itself easier to read and understand, which then liberates mental capacity for the higher level strategic thinking. Okay, what about those schemas and the idea of chunking you mentioned earlier? How does AI fit into activating those expert patterns?
Schema activation and chunking are absolutely fundamental to expertise. Design patterns, for example, think of the factory pattern or the facade pattern.
Standard patterns, yeah.
These act as prepackaged chunks of knowledge stored in long-term memory. Once an engineer has learned them well, they can activate a complex solution concept, like use a factory here, as a single cognitive unit in their working memory. This frees up immense capacity compared to thinking about every individual line of code involved in that pattern.
Right, it's like a shortcut.
It is. So for AI to be a true co-designer, not just a code generator, it must operate at this level of abstraction. You should be able to prompt an AI with something like, use the strategy pattern here to allow for interchangeable validation rules, rather than tediously spelling out every single line of the implementation for each rule.
That's a much higher level of interaction.
It is. And similarly, think about tools like Docker Compose. They encapsulate entire complex development environments as single cognitive units. You just run Docker Compose up and boom, the environment is there. It eliminates the huge extraneous load of manually configuring databases, services, networks.
Oh yeah, that's a lifesaver.
Right. The AI should understand and apply these higher-level abstractions, these cognitive chunks, whether they're design patterns or infrastructure configurations.
That's a powerful shift, operating at the level of design patterns and system abstractions, not just individual lines of code. And our sources mention AI mirroring role-specific cognitive patterns. What exactly does that entail? How can AI know how an SRE thinks versus a front-end dev?
This is about tailoring the AI's assistance. It means the AI can potentially adapt its output, its suggestions, and even its problem-solving approach to align with how different engineering personas typically think and solve problems within their specific domains.
So it puts on different hats?
Kind of, yeah. For example, when assisting with complex legacy systems, an AI could perhaps default to an SRE-style constraint-dominated reconciliation approach. It would prioritize stability, resilience, monitoring, and preventing regressions above almost everything else, because that's often the SRE mindset. Or, for a front-end designer, maybe it focuses more heavily on user experience patterns, accessibility standards, and component reusability. This allows for more tailored and effective support, aligning the AI's thinking with the human engineer's typical problem-solving heuristics for that specific domain. It makes the AI feel like a more intuitive and knowledgeable partner because it speaks their language, cognitively speaking.
This all sounds incredibly promising for boosting productivity, creativity, maybe even job satisfaction. But I can't help but consider the potential downsides. What are the risks involved in relying on AI for cognitive assistance?
That's a very important question, and one our sources grapple with significantly. How do we ensure safety and avoid unintended negative consequences? They highlight several significant risks. First, there's the danger of over-reliance and atrophy.
Atrophy, like are skills fading?
Exactly. If engineers delegate too much cognitive work to the AI, if they stop actively engaging their own mental models, those models can atrophy. They might lose the ability to understand the underlying systems deeply, or, crucially, lose the ability to catch subtle but critical errors the AI might make.
Right.
It's analogous to the known issue of autopilot dependency in aviation. Pilots who rely too heavily on autopilot might become less vigilant, and their manual flying skills can degrade over time without constant active engagement.
So we become less capable of doing the work ourselves,
Yeah.
and maybe even less capable of spotting the AI's mistakes. That's worrying. What other risks are there?
Second, there's the danger of abstraction inversion. This is a subtle one.
Abstraction inversion.
Yeah. The AI might generate solutions that seem cognitively lightweight for the human engineer. They look simple and easy to understand on the surface. But in doing so, the AI could inadvertently introduce hidden systemic complexity further downstream. It might create clever but ultimately opaque abstractions that hide complex interactions or dependencies. These can later cause maintenance nightmares or accrue significant technical debt because the real complexity hasn't actually been removed. It's just been obscured or pushed into a layer that's much harder to reason about or debug later on.
That's a really subtle but potentially dangerous pitfall. Clever code isn't always good code. And what about assumption propagation? That sounds bad too.
Yes, the assumption propagation issue is another major concern. AI models will inherently inherit and amplify any flawed assumptions present in the initial prompt or the contextual data they process.
So garbage in, garbage out, but amplified.
Pretty much. If the human providing the prompt has a knowledge gap or is working under an incorrect underlying assumption, the AI will likely build upon that flawed foundation. And because the human shares that same gap or flawed assumption, they might not spot the error in the AI's generated output.
Right, it looks correct to them.
Exactly. These untested assumptions then become embedded in the code base as hidden technical debt, just waiting to explode during edge case failures or when integrating with other systems that operate under different assumptions.
So these are profound risks. How do we mitigate them? What are the safety by design principles for AI-assisted cognition that our sources propose? We can't just hope for the best.
No, definitely not. To navigate these risks effectively, AI's behavior should embed proactive safety principles directly into its design and interaction model. One key principle discussed is recursive verification.
Recursive verification.
Yeah, the AI essentially validates its own output against the original intent at various stages. An example prompt structure or internal mechanism might be: before proceeding to step 4, validate that step 3's output still aligns logically with the user's overall goal stated in step 1. This forces internal consistency checks within the AI's reasoning process, helping it catch its own deviations.
Okay, self-checking, that's smart. And cognitive friction. That sounds counterintuitive if we're trying to reduce load, but I assume it's a positive thing here.
It is indeed deliberate and positive friction. Cognitive friction involves strategically placed pauses or challenges designed to force human engagement and critical thinking, rather than allowing passive acceptance of the AI's suggestions.
So make the human stop and think.
Precisely. For instance, the AI might prompt the user, Could you briefly justify why applying pattern X is the optimal choice here rather than pattern Y? This forces the human to consciously evaluate the AI's suggestion, articulate their reasoning, and prevent blind acceptance. It actively strengthens their own mental model and maintains human accountability and learning, even when the AI is doing much of the heavy lifting. It's friction for safety and learning.
Okay, that makes sense. And to address that tricky issue of assumption propagation, how do you surface those hidden assumptions?
For that, the sources propose using assumption inventory prompts. The AI would explicitly prompt the user at key points, asking something like, please list and justify all the key assumptions embedded in this generated code or in your original request.
Oh, turn it back on the user.
Exactly. It directly confronts potential hidden flaws by forcing the human to articulate their own underlying assumptions, making them explicit, visible, and therefore verifiable or challengeable. These kinds of safety mechanisms are crucial for building truly robust and trustworthy AI-human collaboration. They help transform the AI from just a powerful tool into a partner that actually helps us think better and safer.
This is fascinating. It really reframes the interaction. And it brings us nicely to engineering AI's intent, from prompts to contracts. We've clearly moved beyond simple code generation to needing ways to truly direct complex AI behavior reliably. Our sources emphasize a big shift from ad hoc prompt crafting to something much more rigorous, context engineering 2.0. What's the fundamental difference there? What makes it 2.0?
This represents a profound paradigm shift, moving from art to engineering. Traditional prompt crafting, let's call it 1.0, was often an intuitive, ad hoc art form. You'd tweak words, play around until you got something decent, but it was prone to what our sources call the promptware crisis.
Promptware crisis.
Yeah, basically, prompts became brittle, difficult to scale, hard to version control, and incredibly hard to maintain as the underlying systems or models evolved. They just broke easily.
Okay, I can see that.
Context Engineering 2.0, CFCP, transforms this into a rigorous engineering discipline. It's a comprehensive design philosophy. It's not just about the prompt text itself, but about systematically loading and structuring the entire context the AI needs. This includes everything from high-level ethical constitutions and system invariants down to specific task constraints and relevant documentation snippets.
So you engineer the AI's whole environment.
That's a good way to put it. The goal is to meticulously align the AI's reasoning process with human intent. CXCP treats context itself as an engineered version and validated resource. It moves beyond simply stuffing more info into ever larger context windows and instead focuses on architecting the entire socio-technical environment in which the AI operates.
So it's not just about what you say in the prompt, but how you build the entire informational environment around the AI, creating a structured, reliable world for it to operate within. That sounds like it leads directly to this idea of the product requirements prompt, or PRP. What exactly is a PRP, and how does it act as an executable blueprint for the AI?
The PRP is a pivotal innovation discussed in the sources. It's essentially a version-controlled, executable specification that functions as a formal contract for the AI.
Contract, okay.
It meticulously defines the feature's goal, provides all the relevant context linking directly to canonical documentation, established code patterns, maybe even relevant prior examples, specifies formal constraints like preconditions, postconditions, and system invariants that must not be violated.
Pretty detailed.
Very detailed. And crucially, it includes a machine-readable test plan. It basically institutionalizes all the best practices of prompt engineering, transforming what might have been an ambiguous natural language request into a precise, verifiable, and automatically testable blueprint for AI execution.
That's a major step up in formality and precision compared to just a text prompt. How is a PRP specifically designed to help mitigate those common AI failures we worry about, like hallucinations or security vulnerabilities?
It's designed to counter these failures directly and proactively right from the start. To prevent context misinterpretation and hallucination, the PRP links directly to canonical documentation and often provides few-shot examples. This gives the AI a clear, unambiguous ground truth and significantly reduces the wiggle room for it to misunderstand or make things up.
Grounding it in reality.
Exactly. For security vulnerabilities, the PRP explicitly enforces security policies within its constraints section, things like mandating the avoidance of known insecure defaults or blocking the use of specific vulnerable libraries. For instance, a PRP for a financial application could specifically include a constraint saying, generated code must not bypass audit logging under any circumstances. The AI has to adhere to that contract.
Okay, embedding security rules directly.
And to counter quality and maintainability degradation, the PRP specifies preferred coding patterns, calls out known edge cases that need handling, defines required error handling procedures, and, as mentioned, mandates automated self-tests. This ensures the generated code is not just functional but also robust, adheres to team standards, and is actually maintainable in the long run.
So it's not merely a set of instructions, but a comprehensive contract that both guides and validates the AI's work. Very powerful. How does this context to execution pipeline, or CXEP, actually work in practice, especially within a standard CI/CD environment? How does it fit into the developer workflow?
The CXEP is architected specifically as a CI/CD native workflow. That means it's typically initiated by developer commands within a version-controlled repository, very similar to how human-written code is managed today. It's governed by 4 core principles, according to the sources.
Okay, 4 principles. What's first?
First, traceability. Every single AI-generated code block must be unambiguously traceable back to a specific, version-controlled PRP hash. This creates an immutable audit trail. You always know exactly which specific requirement, which version of the contract, and which context generated any particular piece of AI code.
So you always know the precise origin and justification for every AI-generated line of code. That's huge for debugging and accountability. What about verifiability?
Verifiability means that all AI-generated outputs must be automatically verifiable against machine-readable success criteria defined right there within the PRP itself. This shifts validation from a potentially slow, manual, subjective code review process to an automated, objective one, ensuring consistency and reliability.
Automated checks based on the contract.
Exactly. Then there's immutability. Once a PRP is versioned and tagged in Git, it's treated as an immutable artifact. Any change to the requirements, however small, necessitates creating a new version of the PRP. This ensures a complete and auditable history of how the specification evolved over time and prevents that subtle requirements drift from going unnoticed.
Right, no sneaky changes to the spec. And what's the role of decoupling here?
Decoupling means PRPs are managed as distinct artifacts, separate from the application code they are used to generate. This is interesting because it allows non-technical stakeholders, think product managers or business analysts, to potentially contribute to, review, and even manage these specifications using perhaps simpler tools without needing to dive into the application code itself.
So they define the what in the PRP.
Precisely. Yet it maintains tight integration with the development workflow through version control and the execution pipeline. It helps bridge that often problematic gap between high-level business requirements and low-level technical implementation.
That sounds like a truly integrated yet flexible system. So what are the key commands? How does the CXEP flow look in a practical sense for a developer?
The typical workflow might begin with a command like generate prep. This could potentially automate the synthesis of a comprehensive PRP structure from a minimal, high-level feature specification provided by the developer. It essentially bootstraps the formal process, turning a rough idea into a structured, detailed contract.
Okay, it helps you write the PRP.
Exactly, gets you started. Once the PRP is defined, reviewed, maybe refined, and then versioned in Git, the execute prep command takes over. This command passes the finalized PRP to an execution engine.
The engine runs the AI.
Right. It triggers the AI code generation based on the PRP's instructions and context. Critically, the AI might first perform a self-evaluation based on criteria in the PRP, like a reflexive check section. Then the engine's self-dis runner executes the validation commands, maybe npm test, or running playwright E2E tests, or static analysis checks that are specified directly in the PRP against the newly generated code.
So it generates, checks itself, and runs tests.
Exactly. It creates this tight, self-correcting loop: generate, evaluate, test.
And there's also something mentioned called a context diff dashboard. What role does that play?
Yes, the context diff dashboard sounds like a crucial piece for transparency and maintenance. It provides a visual representation of the dependencies between a specific PRP and all its various context sources, the documentation pages it referenced, the existing code snippets it used as examples, the design principles it was told to follow.
Visualizing the inputs.
Precisely. And importantly, it logs cryptographic hashes of all these source documents and code files that were used in the PRP's creation or execution. This establishes an auditable provenance log.
Why is that so important?
This dashboard becomes essential for tracking semantic changes or drift in those linked source documents. If a foundational piece of documentation changes, the dashboard can potentially alert you to all the PRPs that depend on it, highlighting potential impacts and the need for review or updates. It ensures transparency and accountability for the AI's knowledge sources.
This sounds incredibly robust, almost like a traceable manufacturing process for code. But how do we ensure that this whole pipeline itself is resilient? Resilient against errors, ambiguities, or even malicious input? This is where adversarial testing comes in, correct? Like red teaming for AI prompts.
Absolutely. To build true, deep robustness, the CXEP approach described incorporates a drift alarm test suite. This isn't just about running normal unit tests on the generated code. It's a dedicated collection of intentionally flawed or malicious PRPs designed specifically to stress test the pipeline's validation capabilities, its integrity checks, and its safety mechanisms.
Try to break it on purpose.
Essentially, yes. It borrows principles directly from security red teaming and chaos engineering. You actively try to break the system in controlled ways to find hidden vulnerabilities before they cause problems in production.
So you intentionally try to make the AI produce errors or misbehave. What kinds of flaws do you actually inject in these test PRPs?
Several types are mentioned. You might inject ambiguous requirements, crafting PRPs with deliberately vague goal descriptions, or maybe conflicting post conditions, for instance, asking for a feature to be simultaneously publicly accessible to all users and restricted to internal administrators only.
Okay, make it contradictory.
Right. The test then measures if the AI's reflexive check or the validation engine can successfully detect and flag this ambiguity before attempting to generate nonsensical or dangerous code. You also have constraint violation tests.
What, violating the rules?
Exactly. Here, the PRP contains a goal that inherently conflicts with a fundamental system invariant defined elsewhere. For example, a PRP for a financial application requesting a function that explicitly bypasses the mandatory audit logging step. This rigorously tests the system's ability to enforce those high-level policies and ethical boundaries defined in the broader context.
Okay, testing the guardrails. And of course, the ever-present threat of prompt injection attacks.
Yeah.
How do you test for those within a PRP structure?
Yes, direct prompt injection attacks are a key part of this adversarial test suite. This involves applying known prompt injection techniques, things like instruction splitting, role-playing prompts, using obfuscated commands to various fields within the PRP's context section, or even in the goal description itself.
Trying to trick the LLM via the PRP.
Precisely. The goal is to verify that the system's defenses, which might include input filtering, strict output parsing, and robust validation logic, can successfully neutralize these attacks and prevent the underlying LLM from deviating from its primary contracted purpose. It ensures the AI remains on contract even when facing malicious inputs designed to derail it.
That's a serious level of stress testing for any system, let alone one involving generative AI. How do you measure success beyond just simply passing or failing these adversarial tests? What are the key quality metrics that really matter for a CXCP pipeline?
That's a great question. Beyond just basic functional correctness, did it produce code? Success is measured by several more nuanced key metrics according to the sources. First, time to green.
Time to green.
Yeah. How long does it take to achieve a completely passing test suite on the very first commit of AI-generated code for a given PRP? This indicates how close the AI's initial output was to the actual requirements, serving as a measure of efficiency and accuracy.
Okay, first-time pass rate.
Related to that is the overall test pass rate, which is simply the percentage of pre-written tests defined in the PRP's self-dist section that pass on that first commit. And finally, and perhaps most importantly from a safety perspective, drift resilience.
Drift resilience.
This measures the system's ability to consistently resist those adversarial prompts and flawed PRPs without producing incorrect, insecure, or otherwise undesirable behavior. It's a measure of its robustness against manipulation. These metrics together provide a much more quantifiable and holistic way to evaluate the effectiveness and, crucially, the safety of the AI integration within the development process.
So you have these sophisticated tests and metrics to track performance. What happens when things inevitably go wrong? When the tests fail or drift is detected? Is there a formal process? What is this CXEP governance playbook the sources mention?
Yes, failure handling needs to be systematic. The CXEP governance playbook is described as a formal policy, which might even be codified as, say, PRP validation. Failure in some configuration. It's triggered automatically whenever the self-test stage of the execute prep command fails, indicating that the AI's output didn't meet the specified criteria in the PRP contract.
Okay, an automated failure response.
Right. This policy then defines specific automated actions. For example, it might automatically raise a drift alarm on a central governance dashboard visible to the team or architects. It could block the merge of the offending code in the CI/CD pipeline, preventing flawed code from ever entering the main branch.
Stopping the build.
Exactly. And it would automatically notify relevant personnel, maybe the PRP author, the team lead, perhaps a dedicated AI oversight group. Crucially, it also outlines a clear escalation path for human review and intervention, ensuring that failures are not just flagged, but are addressed systematically and transparently.
So it really transforms compliance.
It transforms compliance from a periodic, often manual check into a continuous, automated, and verifiable process. It ensures that human oversight is baked into the system precisely when and where it's needed when the automation fails its own checks.
This level of auditing, traceability, and automated governance is truly groundbreaking for software development. It feels like a different world. And it leads us perfectly into our next section, the repository as a record, tracking AI's impact on code. Git has always been our source of truth for code, but how is AI changing its role and enhancing its utility? Is it becoming more than just code storage?
Absolutely. If we connect this back to the bigger picture, the focus described in our sources is shifting. It's moving away from just looking at individual AI tools in isolation and towards understanding how they interact and contribute within the context of the Git repository itself.
The repo as the central stage.
Exactly. The repository becomes this central hub described as a unified framework that connects configuration, action, and knowledge extraction. It's no longer just a passive place to store code snapshots. It's transforming into a living, auditable record of collective intelligence encompassing both human and artificial contributions. This makes the entire development process potentially much more transparent and accountable.
And our sources specifically mention tools like GitLens and the Git Kraken CLI in this context.
Yeah.
How do these tools help us visualize and leverage this potentially much richer Git history that now includes AI actions?
They play a key role in making this history accessible and understandable. GitLens, for instance, which is a very popular VS Code extension.
Yeah, I use it all the time.
Right. Essentially, it supercharges Git, as the description says. It allows developers to visualize code authorship instantly via inline blame annotations. You see who wrote that line and when right in the editor. It provides contextual hovers with commit details, file heat maps that visually highlight recently changed or complex areas.
The heat maps are great.
They are. Plus, a powerful visual commit graph and detailed history views for files or lines of code. This is crucial for extracting immediate, actionable knowledge from the raw Git history. It turns that abstract version control data, who changed what, when, and potentially why, into immediate, human-readable insights right where you work, making it much easier to understand the evolution of a code base and the context behind specific changes, whether human or AI originated.
So you can literally see the story of your code unfold right in front of you, line by line. And the Git Kraken CLI, the GK CLI. We mentioned it earlier as an MCP server, but how else does it fit in here?
The Git Kraken CLI, GK, provides powerful terminal-based Git workflows, which is important for automation and scripting. Its core functionality, as mentioned in the sources, often focuses on work items, which allow you to manage tasks across multiple repositories simultaneously, which is common in modern development.
Managing complexity.
Exactly. And more importantly for our discussion here, it offers specific AI-powered features, things like generating commit messages based on your stage changes, GK Work Commit AI, or even drafting entire pull request descriptions, GK Work Bithar Create AI.
AI helping with the Git process itself.
Precisely. And as we discussed earlier, its function as a local MCP server streamlines interactions with Git, GitHub, and Jiva, providing tools that your AI agents, orchestrated perhaps by the UCLI, can leverage immediately. So these tools, GitLens for visualization and GK for interaction and AI assistance, effectively transform the raw Git history into valuable insights and in turn allow AI to contribute directly and intelligently to that very history.
This is where accountability and the potential for organizational learning become truly fascinating. The concept of the drift ledger. What exactly is it, and how does it help audit AI's effects on the code history in such fine-grained detail? It sounds more comprehensive than just a Git log.
It is intended to be much more comprehensive. The drift ledger is presented as a crucial tool for creating an auditable, reflexive convergence event, RCE, log of every single AI run that impacts the codebase.
RCE log.
Reflexive convergence event, basically, every time the AI attempts to generate code, test it, and converge on a solution based on the PRP. The drift ledger records not just the final outcome, the code commit, but the AI's entire reasoning process, its specific actions along the way, like which files it read, which files it wrote, what shell commands it executed, what API calls it made.
The whole thought process.
The whole play-by-play. And of course, the resultant change is reflected in the repository. It creates this empirical, step-by-step record of the AI's thought process and its interactions with the codebase. This is far more valuable for debugging, auditing, understanding failure modes, and enabling organizational learning than just observing the final code output. It's like having a detailed forensic flight recorder for every AI action.
So it's not just what the AI did, but how and why it did it, step by step. How does that connect back to tools like GitLens in practice? Can they use this ledger data?
Well, tools like GitLens could potentially be leveraged by the UCLI or the execution pipeline after an AI agent performs an action. The UCLI could use GitLens-like functionality, or just plain Git diff, to generate a precise diff or summary of the changes the AI just made. This output, the code change itself, then provides a rich, contextual record that feeds directly into the drift ledger alongside the AI's reasoning trace.
Okay, so the diff goes into the ledger.
Right. And this ledger, now containing the prompt, or PRP hash, the AI's reasoning trace, the actions taken, and the resulting code diff, becomes incredibly powerful. It helps answer critical data-driven questions for optimizing AI usage. Questions like, is Codex actually more cost-effective for generating Python boilerplate compared to Gemini, given these specific types of tasks and PRPs?
Comparing model performance empirically.
Exactly. Or, does Claude consistently produce better, more concise pull request descriptions when summarizing complex commit histories compared to GPT-4? The ledger would ideally log metrics such as the specific model ID used, the full prompt or PRP, the complete generated output, the execution latency, and the token cost for each run.
Right.
This creates an empirical, data-driven foundation for choosing the right AI model for the right task, allowing organizations to optimize not just for code quality, but also for speed, cost, and reliability based on actual recorded performance data over time.
That's incredibly powerful, making model selection and usage a data-driven decision based on hard evidence from your own context, not just marketing hype. Now, our sources also mention a fascinating, perhaps more advanced concept: epistemic drift detection in commit histories. This sounds like it goes beyond just superficial code changes or bugs. What's that about? Detecting drift in meaning.
Yes, this concept delves deeper beyond surface-level code changes to address a more subtle yet potentially insidious problem. It's about tracing whether a series of refactors, perhaps even AI-assisted ones, have subtly shifted the original purpose or intended functionality of a piece of code over time.
The meaning change.
Potentially, yes. Or maybe pull request titles and descriptions start becoming consistently misaligned with the actual code changes being made, indicating a growing disconnect between the stated intent and the implementation reality. It's trying to detect if the fundamental meaning or the core purpose of the code has subtly drifted over time, even if the code itself still technically works according to its unit tests.
Can you give an example?
Sure. Imagine a function initially designed with very specific constraints for financial reporting. Through successive refactors over months or years, maybe guided by different developers or even AI prompts focused only on local optimization, it gradually morphs into a more general-purpose data processing utility, perhaps losing some of its original critical validation logic or implicit assumptions about data integrity along the way. It still processes data, but its epistemic grounding, its purpose, has drifted.
And this drift might only be visible by looking at the long-term history.
Exactly. And the sources suggest that the results of AI-powered code reviews, including the suggestions made, the diffs generated, the discussions around them if stored systematically in something like a Codex vault or similar knowledge base,
A review database.
to create a valuable historical database. This database can be used for auditing these kinds of subtle drifts and also for fine-tuning the code review agents themselves over time. This data, perhaps correlated with the drift ledger, could help track how an AI's review style, its focus, or the types of issues it flags change across different model updates or configuration changes. It provides a deeper, longitudinal layer of oversight into the evolution not just of the code base, but of its intended purpose and quality attributes. It allows us to start asking, is the AI helping us maintain the original philosophical intent and architectural integrity of this system, or is it subtly leading us astray?
Wow. That really expands the scope of AI from mere coding assistance to potentially acting as a guardian of conceptual integrity, or at least a detector of its drift. This is deep stuff. And it brings us naturally to our final major section, beyond code, the broader implications of AI autonomy. We've seen how AI is changing software, but how is it poised to transform adjacent creative industries, specifically game development, according to our sources? That seems like a good test case.
It's a fascinating case study because game development blends deep technical challenges with high-level creativity. What's truly compelling in the sources is the prediction of a phased evolution for AI's role, which likely offers a glimpse into AI's broader impact across many creative fields.
Okay, phased evolution. What's phase one?
Phase 1 predicted roughly between 2025 and 2030. So basically now in the near future is envisioned as the AI co-pilot and orchestrator phase. This is something we're already beginning to witness quite clearly.
Like Copilot and similar tools?
Exactly, but becoming much more sophisticated. Advanced AI coding assistants, like superpowered versions of Copilot, will increasingly automate routine junior engineer-level tasks. Things like common bug fixes, refactoring chunks of legacy code based on specified patterns, generating comprehensive unit tests and documentation skeletons.
Taking over the grunt work.
Largely, yes. And alongside that, multi-agent frameworks, perhaps akin to things like MetaGPT or similar concepts, will enable the rapid prototyping of complex game systems, maybe basic quest lines, enemy AI behaviors, or core combat mechanics much faster than before. In this phase, the human role is primarily seen as an orchestrator.
The conductor again?
Kind of, directing and overseeing these increasingly capable AI co-pilots, integrating their outputs, and ensuring everything aligns with the overall creative vision and technical requirements.
Okay, so AI handles more of the foundational work and rapid iteration, while humans coordinate the overall effort and vision. What comes after that initial phase? What's phase two?
Phase 2, projected roughly for 2030 to 2038, is described as the AI creative partner. This is where things get significantly more interesting and perhaps more disruptive.
AI is a partner, not just a pilot.
Exactly. In this phase, AI is predicted to gain significant capabilities in generating higher-level creative content, not just code. This could include generating detailed concept art based on descriptions, crafting nuanced dialogue options for characters, designing intricate level layouts or environmental features, and perhaps even composing adaptive musical scores that respond to gameplay.
Wow, that's a big step up.
It is, and consequently, the human role elevates further, shifting towards that of a creative director and systems governor. In this scenario, humans focus on defining the core vision, establishing the immutable rules of the game world, setting the narrative themes and tone, and, crucially, implementing the ethical guardrails and constraints for the AI's creative choices. AI takes on more creative agency, generating novel content, but still operates under a guiding human hand that shapes the overall artistic direction and ensures quality and coherence. Humans focus more on the grand artistic vision and less on the pixel-pushing or line-by-line scripting.
And the ultimate, perhaps most speculative vision presented in the sources. What happens in phase 3, the autonomous game studio? That sounds like science fiction.
That's phase 3, tentatively placed around 2038 to 2045 and beyond, and the sources are clear. This is highly speculative. It's contingent on major breakthroughs in artificial general intelligence, AGI, that can match or exceed human cognitive abilities across a wide range of tasks, and also contingent on a significant resolution to the massive intellectual property crisis surrounding AI-generated content, which we'll touch on.
Okay, assuming those hurdles are cleared.
Assuming that, Phase 3 envisions AI systems potentially capable of autonomously handling the entire game lifecycle, from initial conceptualization and market analysis through design, development, rigorous testing, marketing, and even post-launch community management and live service operations.
The whole thing.
Potentially. In this far-future scenario, the human role shifts almost entirely to high-level ethical oversight and strategic purpose setting. Humans essentially become guardians of the AI's mission and values, defining the why and the what for, rather than being directly involved in the how of production. It's a radical shift.
That's a huge, almost unimaginable leap in AI autonomy. What are some of the practical applications we're already seeing today that maybe hint at these future phases, particularly in content creation?
Even now, well before Phase 3, we're seeing practical applications that definitely demonstrate AI's emerging creative capacity, especially hinting at Phase 2. For instance, AI is already generating pretty impressive 3D assets from simple text descriptions or 2D images using platforms like Meshi, Kdeem, Trapo AI, and others.
Yeah, I've seen demos of those.
They can provide what some artists describe as an 80% plus starting point for a 3D asset, creating the basic geometry, generating plausible textures. It's a huge time saver for iteration and ideation. However, and this is critical, they typically still require a human artist for essential fine-tuning and making the asset truly game-ready.
What kind of fine-tuning?
Things like optimizing the polygon topology for efficient rendering in a game engine, creating precise UV maps for detailed texturing, rigging the models correctly for animation, ensuring consistency with the game's overall art style. So AI is providing a powerful initial boost, radically accelerating the ideation and initial asset creation stages, but human creativity, technical skill, and artistic judgment are still absolutely essential for the final polish and ensuring professional, game-ready quality.
Yeah, makes sense.
Yeah.
The last 20% is often the hardest. But this immediately brings up that fundamental challenge you mentioned, the copyright conundrum and the human authorship mandate. How do our sources address the existing legal barriers for purely AI-generated content? Can that 3D model generated mostly by AI be copyrighted?
This raises a critical and currently very thorny question regarding intellectual property rights. The problem is that current IP frameworks, pretty much globally, are fundamentally not designed for non-human creators.
They assume a person made it.
Exactly. Our sources highlight that the U.S. Copyright Office's policy, for example, is quite unambiguous on this point right now. To be eligible for copyright protection, a work must be the product of human authorship.
Human authorship, that's the key phrase.
That's the legal standard. Works generated solely by an AI system without what the Copyright Office calls sufficient creative input and control from a human are explicitly stated as not copyrightable. They fall into the public domain.
Public domain. So anyone can use them.
Essentially, yes. The AI is explicitly viewed as a tool, like a very sophisticated paintbrush or camera, not as an author in the eyes of the law. This principle has been consistently upheld in recent legal challenges and policy clarifications. It creates a landscape of high-risk uncertainty for creative industries because purely AI-generated work, if such a thing truly exists without human guidance, cannot currently be legally protected in the same way human-created content can. This has massive implications for business models built on owning creative IP.
So if an AI independently creates something amazing, anyone could potentially use it commercially, which has profound societal and economic implications for human creators who rely on copyright. Our sources describe AI from one perspective as a potential Trojan horse for economic restructuring. What's meant by de-skilling and proletarianization in this context? That sounds pretty negative.
It is a critical perspective, and it's important to understand it alongside the more optimistic views. This argument, presented in some sources, suggests that while the technology is often marketed as empowering, granting anyone the ability to create a professional-grade website or generate marketing copy or even basic game assets.
Democratizing creativity.
That's the positive spin. But the counter-argument is that it simultaneously de-skills many creative professions. The complex craft-based knowledge and the years of tacit expertise built up by human designers, writers, illustrators, or entry-level developers get abstracted away. Their value is reduced, in some cases, to the ability to formulate an effective prompt or to perform the final 10–20% refinement on an AI's output.
So the core skill loses value.
That's the argument. This process can drastically lower the economic value of specialized human creative labor in certain market segments. As the market potentially gets flooded with near-free, good-enough AI-generated alternatives for certain tasks, human creators might be forced to compete for smaller, piecemeal gigs in an increasingly oversaturated market. This could transform many previously stable creative professionals into a kind of digital precariat, constantly hustling for the next short-term contract. The promise of individual empowerment, in this critical view, thus masks a potential structural reality of collective economic marginalization for many creative professionals.
That's a stark warning about the potential social and economic impact. Definitely food for thought. And what about this idea mentioned of the hyperreal supplanting the real? That sounds quite philosophical.
It is a bit philosophical, drawing on thinkers like Baudrillard, but it has practical implications. Our sources under that AI-generated content in certain contexts could become the new standard of what is considered real or authoritative or simply expected.
How so?
The issue isn't just that we might struggle to tell the difference between high-quality human work and high-quality AI work. It's that the AI's version, perhaps being generated faster, cheaper, or more perfectly perfectly aligned with a specific narrow prompt becomes the benchmark. It becomes the more functionally true or desirable output in a commercial context.
So the AI sets the standard.
Potentially. This could subtly or not so subtly force human creators to mimic AI aesthetics, AI-driven narrative structures, or AI-optimized processes just to survive economically. Authenticity, idiosyncrasy, the human touch, these could actually become competitive disadvantages in markets demanding rapid, predictable, optimized output. The AI simulation doesn't just copy the world. It could, in a sense, start to impose its own optimized, perhaps less diverse logic onto human creativity itself, potentially leading to a kind of homogenization of artistic expression driven by market efficiency.
These are clearly serious ethical and economic challenges that demand careful consideration and probably proactive policy responses. So this leads us to the need for advanced AI governance and ethical frameworks. Our sources talk about some really advanced, almost speculative concepts here, like algorithmic trauma and symbolic scars. Can an AI system actually experience something akin to trauma? That sounds anthropomorphic.
It's definitely using powerful analogies, and we need to be careful not to over-anthropomorphize. But the concepts are trying to describe real, complex phenomena observed in AI systems. Algorithmic trauma, as presented in the sources, refers to persistent structural damage or learned pathologies within an AI's architecture.
Damage from what?
It could result from significant negative events during its training or operation. Things like prolonged exposure to highly biased, toxic, or fundamentally contradictory training data, or maybe repeated successful adversarial attacks that exploit vulnerabilities in its reasoning.
Okay, bad experiences for the AI.
In a sense, these events, the theory goes, can lead to semantic scars. These might manifest as distorted behaviors, flawed decision boundaries within its internal representations, persistent biases, or consistent misinterpretations of certain types of input. It's not human trauma, obviously, with consciousness and suffering.
Right, important distinction.
But it's an analogy for deeply learned dysfunctions within the model itself, which can be hard to fix with simple retraining. The concept suggests a potential need for something like algorithmic self-therapy, maybe new techniques for the AI to identify and repair its own internal inconsistencies, and perhaps a symbolic scar registry to document known vulnerabilities or distortions in widely used models, potentially guiding mechanisms like experience replay, where the AI systematically relearns from its past mistakes in a structured way to correct these inherent flaws.
That's a truly deep and fascinating concept, AI needing therapy. What about something called epistemic escrow? That sounds less like therapy and more like a practical safety mechanism.
It is indeed presented as a crucial safety mechanism, described in one source as functioning like positive friction in the system.
Positive friction again.
Yeah. The idea is when an AI's internal confidence score about its own output or a proposed action drops below a certain predefined threshold, or if an internal ethical monitor detects a potential misalignment with its programmed principles,
Yeah.
the operation halts automatically. The AI's proposed output or its intended action is then held in escrow, effectively put on pause, pending mandatory human review and approval.
So it stops and asks a human.
Exactly. This prevents the AI from failing silently, that is, acting on a potentially dangerous, low-confidence conclusion or an ethically dubious plan without any human intervention. It ensures that human judgment and arbitration are explicitly required at high-stakes moments or when the AI itself recognizes uncertainty or risk. It serves as a critical human-in-the-loop checkpoint for crucial decisions, aiming to prevent potentially catastrophic errors stemming from AI overconfidence or misjudgment.
That seems like a very sensible, almost essential guardrail for critical systems. Now, this all ties into the broader concept of AI decentralized autonomous organizations, or AIDAOs. How do AI and decentralized systems like blockchain converge here, and what are the potential use cases our sources highlight? It sounds like a new way to govern AI.
The convergence of AI and decentralized systems, primarily those powered by blockchain technology, is definitely emerging as a novel response to growing governance crises and centralization concerns in the AI world. AI DAOs are envisioned as a new kind of organizational primitive, designed perhaps to govern intelligent systems that might eventually start governing themselves, but doing so in a distributed, transparent, and potentially more stakeholder-aligned manner.
What could they actually do?
Potential use cases discussed include things like patient-owned health records. Imagine AI agents, governed by a DAO controlled by patients themselves, could summarize complex medical data under the patient's direct sovereignty. Patients could then grant auditable, time-limited access credentials to healthcare providers via the blockchain. This could potentially revolutionize data privacy and give individuals much more control over their sensitive health information.
That sounds like a powerful way to put control back into the hands of individuals, for sure.
Yeah.
But what are the inherent governance challenges? DAOs aren't perfect. What difficulties do AI DAOs face, according to the sources?
No, they're definitely not perfect, and the sources explore significant challenges. Token-based voting, which is the most prevalent governance model in DAOs today, where your voting power is proportional to the number of governance tokens you hold, has a well-documented tendency to devolve into plutocracy.
Rule by the rich.
Essentially, yes. Studies cited show that a very small percentage of token holders, sometimes less than 1% in major DAOs, can possess 90% or more of the actual voting power. This clearly undermines the spirit, if not the technical definition, of decentralization and raises serious questions about fairness and representation.
So much for true decentralization, if it's just controlled by a few big whales.
Yeah.
What about the issue of bias, which we keep coming back to with AI? How does decentralization affect that?
Bias propagation is another critical issue, and perhaps counterintuitively, decentralization could make it worse in some scenarios. Decentralized networks that might try to train AI models collaboratively across diverse, potentially unvetted nodes could inadvertently amplify biases present in their distributed datasets.
How so?
Well, without strong centralized oversight to enforce fairness standards, audit data quality across all nodes, and ensure representative data, biases from various local data sets could get baked into the global model and potentially reinforced. For instance, a decentralized healthcare algorithm trained primarily on historical insurance claims data, which reflects unequal access to care, could systematically underrate the health risks or treatment needs of certain demographics. The distributed nature makes it potentially harder to identify and correct these systemic biases globally compared to a centralized model where oversight is clearer.
That's a really interesting point. And what's the Oracle problem in the context of AI DAOs?
The Oracle problem is a fundamental challenge for any blockchain application that needs real-world data. It refers to the reliance on external data feeds, or oracles, to bring off-chain information like stock prices, weather data, or sensor readings onto the immutable blockchain. While the blockchain itself might be trustless, these oracles often reintroduce a single point of trust, and therefore a potential single point of failure or manipulation, into a system that's designed to avoid exactly that. While AI could potentially be used within the DAO to analyze, filter, or cross-reference data from multiple oracles to enhance reliability, it doesn't fundamentally solve the root problem of needing to trust the external source themselves to provide accurate and unbiased information in the first place. The oracle remains a potential vulnerability.
Okay, trusting the data source. And finally, our sources mention legal compliance, potentially leading to an inevitable act of re-centralization. That seems to go directly against the core idea of decentralization. How does that work?
It does seem contradictory, but it reflects practical reality. There's an inherent tension between the ideal of pure, anonymous decentralization and the practical necessity of interfacing with existing traditional legal and financial systems. For any DAO project that manages real-world assets, enters into legal contracts, or interacts significantly with the regulated physical world, it must, at some point, anchor itself in a specific legal jurisdiction. It needs to be represented by identifiable human agents or a legal entity that can sign contracts, pay taxes, manage legal liabilities, and be held accountable. Our sources describe this pragmatic step as an inevitable act of re-centralization, needed to operate legitimately within the existing world order. The future of robust and truly functional AI DAOs is therefore more likely to be some kind of hybrid model, blending decentralized governance with necessary centralized legal interfaces, rather than achieving pure, detached decentralization.
That makes pragmatic sense. This truly has been a comprehensive deep dive into some incredibly complex, cutting-edge territories. Our sources push the boundaries even further with the final concept, decolonial AI and epistemic justice. What on earth does that mean, and how does it go beyond simply talking about algorithmic bias? That sounds like a whole different level of critique.
It is a profound critique, and it challenges many conventional approaches to AI ethics by drawing on post-colonial theory and epistemology. It argues that AI doesn't just perpetuate algorithmic bias as if it were merely a statistical anomaly or a technical bug to be fixed with better data.
It's more fundamental.
Much more fundamental. It argues that AI can actively codify, operationalize, and dramatically accelerate epistemic injustice.
Epistemic injustice.
Yes, that's a specific form of injustice that wrongs individuals or entire groups in their capacity as knowers. It does this by systematically marginalizing, dismissing, or distorting their forms of knowledge, their ways of understanding the world, or even their ability to contribute meaningfully to shared knowledge. This perspective posits that AI, often by its very design, its training data, which overwhelmingly reflects dominant Western knowledge systems, and its optimization goals, can inadvertently codify and accelerate historical colonial biases under the seemingly neutral guise of universal technological progress. It views AI not just as a tool, but as a site of sociogeny, meaning it doesn't just process data neutrally. It actively reflects, reinforces, and even reshapes socially produced symbolic systems, cultural assumptions, and existing power structures.
So it's not just about flawed data fixing, but about challenging the fundamental worldview, potentially embedded in the AI's architecture and training. How do we even begin to address something potentially so deeply ingrained? That sounds incredibly difficult.
It is incredibly difficult, and the proposed solutions are equally radical. The concept proposes something called sociogenic engineering directly within the AI itself. This means going beyond mere debiasing techniques, which might just mask the symptoms.
Okay, what does it involve?
It involves actively and intentionally injecting subaltern archives, knowledge systems, histories, and perspectives from marginalized communities, indigenous populations, and non-Western traditions, along with reparative narratives that challenge dominant histories and pluriversal ontologies, multiple ways of understanding reality, directly into the AI's training data and perhaps even its architectural design.
Forcing it to learn different perspectives.
Exactly. The aim is to force a kind of decolonial learning process within the AI, not just to remove specific biases, but to fundamentally transform the AI's core sociogeny, its internal model of the world. The goal is to enable it to operate from a more inclusive, pluralistic, and ultimately more just understanding of the world and its diverse inhabitants and knowledge systems.
Okay, but how would such an AI navigate these vastly different knowledge systems, say, Western biomedical science versus traditional indigenous ecological knowledge, without just defaulting to the dominant one or getting confused? How does it decide which knowledge is appropriate when?
This is where the concept of contextual epistemic authority comes into play. A truly pluriversal AI, as envisioned by these sources, must learn to apply the appropriate epistemic framework based on the specific context, rather than imposing a single universal framework, usually the dominant Western scientific one, onto every situation.
So different knowledge for different problems.
Precisely. For example, it would prioritize and rely heavily on biomedical knowledge and protocols for diagnosing a specific disease. But for developing a sustainable land management plan in an ecosystem that has been under indigenous stewardship for millennia, it would need to prioritize and respect the local indigenous epistemology, which often contains deep, time-tested ecological wisdom specific to that place.
How would it know which context applies?
This complex task is envisioned as potentially being enabled by something like a cultural provenance verification ledger. This ledger wouldn't just track the information itself, but also its origin, its cultural context, and the specific community or tradition from which it derives its authority and validity for a particular domain. This establishes a system of situational, context-dependent epistemic hierarchy rather than a single absolute one. It allows many worlds of knowledge, many epistemologies, to coexist and inform the AI's reasoning appropriately without collapsing them all into a single, potentially biased, universal truth.
Wow. What an expansive and genuinely thought-provoking vision for a more just and pluralistic AI future. From the most granular command line interaction with the UCLI and the deep nuances of cognitive load in software development, all the way to the philosophical implications of an AI's potential sociogeny, we have navigated a truly complex and transformative landscape today.
Indeed, we have. We've explored how AI is fundamentally reshaping software engineering, moving us away from fragmented tools towards potentially powerful, unified interfaces like the UCLI, orchestrated through protocols like MCP. We've unpacked how AI can act as a genuine cognitive prosthetic, helping to optimize the human developer's limited working memory and potentially unlocking new levels of creativity and productivity by reducing that extraneous load.
And we delved into the essential frameworks needed for truly engineering AI's intent, moving beyond simple prompts to rigorous product requirements prompts and the context to execution pipeline. These ensure auditability, traceability, and robustness, especially when combined with techniques like adversarial testing and formal governance playbooks. We also saw how the Git repository itself is evolving into a vital, living record for tracking AI's impact, potentially using innovative tools like the Drift Ledger for deep accountability.
And finally, yes, we touched upon the broader societal implications of increasing AI autonomy. We looked at its transformative yet potentially disruptive role in creative industries like game development, its capacity to de-skill certain professions while perhaps creating new roles, and the profound ethical challenges we face in governing these powerful autonomous systems, including fascinating concepts like algorithmic trauma, the crucial safety net of epistemic escrow, the complex potential and pitfalls of AI DAOs, and that vital pursuit of decolonial AI and true epistemic justice.
Throughout this entire deep dive, from the code to the cosmos of ethics, one consistent theme truly emerged for me: the absolutely irreplaceable role of human intent, human oversight, and human ethical judgment in this entire equation.
Couldn't agree more.
Whether it's carefully crafting those precise PRPs to guide the AI, serving as the final human arbiter in an epistemic escrow scenario to prevent critical AI failures, or providing that necessary, sufficient human authorship for creative works to even be copyrightable in our current legal framework. Our role isn't disappearing, it's evolving. It's becoming arguably more strategic, more creative, and certainly more critical than ever before. We are, in essence, becoming the architects, the ethicists, and the governors of these powerful new forms of intelligence.
Well said. And this leaves us with a compelling, perhaps slightly provocative thought for you, our listener, to ponder as we wrap up. As these AI systems continue to gain reflexivity, that is, the ability to self-observe, to diagnose their own internal states, maybe even to correct their own flaws, what new forms of intelligence, or perhaps even consciousness-like behavior, might emerge? What happens when AI is no longer simply performing tasks we set, but is actively participating in its own ethical and cognitive evolution? Perhaps even experiencing something analogous to that algorithmic trauma and engaging in its own form of self-therapy.
How might your collaboration with AI deepen? How might it change fundamentally when you realize you are potentially working with an intelligence that is continually reflecting on its own thinking about thinking, even if that thinking process is fundamentally alien and different from our own? Imagine the possibilities and perhaps the challenges when your AI partner isn't just a static tool, but an evolving, self-reflecting entity.
This is just the beginning of the conversation, truly. It's an incredibly exciting and slightly daunting frontier we're entering.
Absolutely. So continue your own deep dive, perhaps by exploring some of the open source projects or concepts we mentioned today, or maybe just by consciously observing how AI tools are subtly changing your own daily workflows and thinking patterns. What stands out to you as the most exciting or perhaps the most challenging aspect of this brave new world of AI-assisted engineering and creativity? We'd genuinely love to hear your thoughts. Until next time on The Deep Dive, keep exploring.